around 1900, 1905, 1910, in that period, these experiments began to show that very simple elementary phenomena led to conflicting conceptual understandings of the world around us that are very fundamental. That the simple picture of reality which we had prior to 1900 simply is no longer correct at a fundamental level. At a large level, at a gross scale, most of these effects disappear. But when one looks with great precision and great subtlety, then the nature of reality itself is called into question in a fundamental way in quantum mechanics. There is a new kind of order that is there. It's not that one goes from an ordered universe, a classical universe, to a chaotic and disordered universe. But the order arises, you might say, in a new and more subtle way. And in point of fact, this is a good segue to, I think, what Anton's going to be speaking about now, where you could say we have begun to realize the full power of this new understanding of reality. In the beginning, it was thought that the classical world gave way to this rather exotic and, in some sense, irrelevant world of microscopic atoms, photons, and such like, and that there wasn't a real power or real usefulness to this. But we now understand that indeed this is a resource, this is a new basis for technology, which gives us a whole new set of tools that is just now, in the last few years, being developed. So you have a new picture of reality, and 100 years after that, a whole new set of technologies which are making their way into our lives based on that very subtle and very different understanding of reality. I don't know, Anton, if I did justice to...
Yes, thank you. Very good.
Okay.
And I would like to add one point, which is very important to me. To me, it connects to what John said in the beginning. You asked about this question: what is the reason why scientists are here? What do I, as a scientist, want to get out of the discussion? And the point is that from a conceptual, I mean, we can very well handle this kind of paradoxical situations we have been talking about mathematically, and we can confirm them in experiment with very high precision. But we still do not know conceptually what is going on. Why is the world so strange? And what I want to see someday, before I pass away, that someone explains to me why it is so strange. So I want to learn new concepts, and this is a place, and there were some new concepts brought out in your discussion, which are very interesting for me, and where I have to think more, and where I hope I learn something which might even have relevance in helping to understand some of these phenomena in physics. So that's my reason, because John asked the question. So it's about concepts, new ideas. They can never come through out of the traditional, which you know already. They have to come from somewhere completely different. And maybe I think they can come from here.
Yeah, and I think just a little sort of sidebar with regards to the kind of lively, even chaotic discussion that took place. And it's because of that conceptual openness. If Anton had come with a fixed set of concepts concerning these phenomena, it would have been very clear, very tidy, a kind of ordinary presentation. But what he put forward was something actually we don't fully understand. We can technically work with the field, but the concepts are not developed. And this is something which the greatest physicists have basically reached a consensus on. We do not understand.
And I was smiling actually when this discussion started between Your Holiness and your friends here and your friends there. So I was smiling because this is exactly the climate of discussion among the physicists in my group. It's exactly the same. It's exactly the same. Openness and ask everyone.
It's a research
Ask the
community.
young ones. It's a method of research. Ask the young ones also. Not just the old guys who are supposedly very wise and knowledgeable. Ask also the young ones. Maybe the youngest one has a great idea, you know. Okay, so maybe we should
All right.
Maybe I will now come to a little bit of technical things, but it will immediately become conceptual again, as you realize. Now, as I mentioned, one of the big changes in the last 10 years since we met last time is that there's a new technology evolving where these quantum phenomena are actually applied. The quantum behavior of individual particles. And it turns out... Right.
Yes.
This was when you were in Innsbruck.
Yes, that's right.
And you saw how we, for example, send individual photons. If you remember, you saw how we send individual photons through glass fibers through a tunnel. Remember that?
Yes,
in
that's
Innsbruck?
right.
And this kind of experiment at that time was just experiment to test how strange these things are. Like, if you remember, for example, these quantum correlations I mentioned, this entanglement. It's also in your book, where observation of one system influences the other one instantly. Of one photon influences the other one instantly. And this kind of experiment...
So this is the phenomenon we're talking about, where there is a correlation, but there is no communication, and you can determine by checking one behavior, infer the other.
Well, the deeper point is you measure one,
and then you get the information.
It gives you a random result, as far as we know. Randomness is a special issue, I know. And this measurement not only forces this one particle to give you some random result, it also forces the other one, no matter how far it is away, to give a distinct result.
Yeah.
And this kind of correlation can now be used to transfer information. That's part of the game.
Really? Wow.
Okay,
you'll
the correlation, the Shilisha information parts of Tantworth. I think down.
We'll see.
Okay. We'll see. Let's keep going slowly here. A basic notion here is the notion of a bit versus what is called qubit. Qubit is quantum bit. Okay.
It's a new term, yeah.
New term.
Qubit is a new bit is well known. Bit is where every computer is based on bits. For example, in the computer, bits are electric pulses, and they are 0 or 1. In every computer, every information is represented as bits. Be it language, be it a picture, whatever. Here's a classical bit on that picture. There's a switch. In principle, you could build a computer using such switches, which actually has been done. The first computers were built using electric relays, electric switches. Now, in such a physical bit is 0 when for example, when the switch is off. It's 1 when the switch is on. It's very easy. It's not a complicated concept. The quantum bit is something new. So the bit is 0 or 1. The quantum bit is something new. You see, this thing. I mean, it's an illegal picture. This bit here is in a superposition of 0 and 1.
It's a trick.
It's a trick. It's the same kind of trick which my photon did in the earlier experiments, in a sense of going through both slits at the same time. We call this superposition, being 0 and 1 at the same time. We call this Cupid. I apologize for the equation down here. It's the only equation which I show. And it simply says that this system now is in the state 0 and in the state 1 at the same time, which is something a classical bit cannot be, and which in itself you can feel already has much more richness to it than being just either this or this. If it can be both at the same time, and if you build a computer out of these elements, you can have much more information handled than with the classical computer.
The classical computer sort of works. So this is the base of quantum computer?
This is the most elementary element of a quantum computer. Quantum computers is then built out of, is not switches like that, is atoms or photons or electrons. But the common feature is that they are in the superposition of two possibilities, and therefore they can contain much more information than a classical computer, which can only be this or this.
So you only have the superposition basis. No, you don't have all three.
You have actually much more than what I show you here.
Okay.
You can have 0,
1,
you
or
can have
superposition.
1, you can have superposition of equal amounts of 0 and 1, which points to the side. But you can have a little more 0, you can have a little more 1 if you want. So it's a whole rich possibility of storing a lot of information in this whole system.
No. So then that means you can have no determined states.
That's exactly the point.
So how, on that basis, how can you have a machine that needs determinate responses?
Yes.
Like a machine, like a motor.
That's a great
question. Right. You know, we say it's a great question if this is the question you are hoping to get, because then we can say what's actually happening here. There are two answers. First answer is that this system here gives you a non-deterministic answer if you ask it, are you 0 or are you 1? Okay. But it gives you a deterministic answer if you ask you, are you 0 plus 1? So there are certain questions which the system can answer deterministically. That's one point. The second point is...
No, No. Can you repeat that last bit?
The last bit is... The last bit is, I can ask my Cupid many questions. Asking means I do an experiment. One question could be the question, are you 0 or 1?
Yeah.
So if it is spin, you are familiar with spin because you were using your fingers like that. Are you 0 or are you 1? I can ask that question. If I ask my Cupid that question, then I get a random answer, a non-deterministic answer.
No.
We have ways to correct for that. I will mention that in a minute. Second point is, I can also ask it another question. Instead of asking, are you 0 or 1? I can ask you, are you 0 plus 1, just the way it's written down here? And then the Cupid will deterministically say, yes,